Hello everyone, and welcome back to another video. Today I'm going to be talking about the squeeze theorem. This is a theorem used to evaluate limits that are not as easily defined algebraically, but relate to limits that we do know how to solve and that we can solve algebraically or that are already known to make the problem a lot easier. The squeeze theorem states that if we have a function, say we're looking for f of x, and we know that f of x is strictly less than some h of x, while also being strictly greater than some g of x. I suppose I should put or equal thens here. Then, when we take the limit as x approaches some number, the idea is to get g of x at this limit as x approaches some a to be equal to the limit as x approaches a of h of x. What this will do is it will force the limit as x approaches a of f of x to be exactly the same as g of x and h of x, because if it's greater than or equal to 1 and less than or equal to the other, but they're both equal, then it has to be equal to both. And so we found our limit. If that was confusing, then let's put it into practice. One of the most famous examples of using the squeeze theorem to solve a limit is the case of the limit as x approaches 0 of sine x over x. If you just plug in 0, then you get 0 over 0. And if you take L'Hopital's rule to differentiate the top and the bottom, it's called cyclic reasoning because the idea of taking the derivative of sine x means you need to take this limit. And I've been over this in a previous video that I made many moons ago at this point. But this limit is basically non-elementary in the normal sense that we've been talking about so far. We can't just use L'Hopital's rule, and we can't just algebraically manipulate it, and we can't just plug in the number, right? So we're going to be using the squeeze theorem to solve this problem. To solve this, I'm going to be using a visual proof. Say we're on the unit circle. We've got a chunk of it right here. Looks like this. And then we create a couple of extra lines. Now, this angle is x in radians. This distance is 1. This distance is sine x. This is cosine x. This greater distance is 1. And so this is tangent x. This is because this is the same triangle but scaled up. The scaling factor goes from cosine to 1, so we're dividing by cosine. And so when you apply that to this, you get sine divided by cosine, which is tangent. Now, there are three things to think of here. This is less than this, but greater than this. Okay, well, what are all these three things? This is sine x, so we know that's going to be our lowest limit. And then tangent x is going to be our top limit. Now, this curve is an arc, and so the arc length is calculated by the angle times the radius. The radius is just 1, and then the angle is just x, so we have x. So we have this inequality set up. Tangent x is greater than or equal to x is greater than or equal to sine x. Now, we need to rearrange this into getting sine x over x. So what we'll do is we'll divide everything by sine x. Since sine x is positive in this case, we don't have to flip any of the inequalities. Tangent divided by sine is, of course, 1 over cosine, greater than or equal to x over sine x, greater than or equal to 1. Now, what we're going to do is we're going to flip all three of these. And when we do that, we will need to change the order of the inequality. Flipping the 3, we'll get cosine x is less than or equal to sine x over x is less than or equal to 1. Now, we will take the limit as this whole thing approaches 0. The limit as x approaches 0 of 1 is still just 1. And the limit as x approaches 0 of cosine x is 1, because you can just plug in the 0. Cosine of 0 is 1. Now, the limit as x approaches 0 of sine x over x is between 1 and 1. So, by the squeeze theorem, we can state that this limit is equal to 1. And that is our final answer and a demonstration of the squeeze theorem. I hope you enjoyed today's video. That proof is one of my favorite proofs in all of mathematics, and hopefully you were able to gain something from it yourself. Good luck in your classes, and as always, thank you so much for watching.